Hello everyone, welcome back to online lecture series on design of machine elements. We are continuing our lectures on pressure vessels. So till now we have covered the introduction, classification of pressure vessels, then the kinds of stresses which are generated in the thin cylindrical shell due to internal pressure. There are two types. First is circumferential or hoop stress, and second is longitudinal stress. We have discussed both. Then we move to thin spherical shells subjected to internal pressure, and the last topic which we discussed was the thick cylindrical shells subjected to an internal pressure. Here we have discussed about Lam's equation, Bernoulli's equation, and Clavrino's equation. So in today's class we will discuss about the compound cylindrical shells. So let's begin. So first of all we will revisit the Lam's equation. The thickness of cylindrical shell is given by this formula. Now if you focus on the denominator of this square root, which is sigma t minus p. So if we purely see this mathematically, then in a case when the value of p is greater than sigma t, that is shown over here, that value of p is greater than sigma t, then in such case the denominator part will be less than 0. So in such cases this will be indeterminate. So if the internal pressure P acting on the shell is equal or greater than the allowable working stress sigma T for a material of the shell, then no thickness of the shell will prevent the failure. So we cannot find a valid value or the natural value of thickness which will be able to prevent the failure. Thus, in such cases, it is impossible to design a cylinder that can withstand internal pressure equal to or greater than the allowable working stress. So, for that we need to provide some special arrangement. So, this is overcome by introducing initial compressive stress on the wall of the cylindrical shell. So let's see that how exactly we can achieve this. So it is done by two ways. First of all, by compound cylindrical shell, which is shown over here, and second is by using the theory of plasticity. Second is theory of plasticity. So in the first method, the outer cylinder, which is having inside diameter smaller than the outside diameter of inner cylinder, is shrunk fit over the inner cylinder by heating and cooling. So if you carefully focus on this portion, that the inside diameter of outer cylinder is smaller than the outside diameter of inner cylinder. It might look confusing for a while, but if you carefully think about this, then let me show you, maybe if I can show you here, that let us say that this is the outside cylinder. Okay, And for the sake of understanding, let us say that this is the inside diameter, that is this one is 2 meter, and let us say that we have another cylinder which is smaller cylinder having, this is the smaller cylinder that we have, consider this as inside cylinder. Okay, and let us say that this inside cylinder outside diameter, that is this outside diameter, this one is, let us say 2.2 meter. So if you think, then in natural circumstances it is not able to fit this inside cylinder into the outside cylinder to make a compound cylinder. That is obvious. Okay, so how it is done? It is done by shrunk fit over the inner cylinder by heating or cooling. So by heating and cooling process, we can make this cylinder to be fitted inside the outside cylinder. So when we cool it, once it is cooled, then the contact pressure is developed at the junction of two cylinders. Okay, contact pressure is developed at the junction of two cylinders, which induces the compressive tangential stress in the material of inner cylinder and tensile tangential stress on the material of outer cylinder. So this statement will get cleared once we derive the stresses. Then you will understand that how exactly the inner cylinder has compressive tensile strength and the outer cylinder has tangential tensile stress. So when the cylinder is loaded, the compressive stresses are first relieved and then the tensile stresses are induced. Okay, so thus a compound cylinder is effective in resisting the higher internal pressure than the single cylinder with same overall dimensions. So they are trying to say here that compound cylinder is more capable of handling the high internal pressures than the single typical cylinder. Okay, now the theory of plasticity says that a temporary high internal pressure is applied till the plastic stage is reached near the inside of the cylindrical wall. This induces, gives residual compressive stress on the removal of internal pressure, thereby making the cylinder more effective to withstand the higher internal pressure. So this portion is not that important because it is not the part of your derivation. So it is just for the sake of information only. Okay, now let's move forward to the stresses in the compound cylindrical shell. So we will derive this theory now. So first of all we will focus on this figure, that if you see, then here we are having a compound cylinder in which this blue shaded portion is the inner cylinder and the red shaded portion is outer cylinder. The inner cylinder has inner radius of R1 and outer radius of R2. Similarly, the outer cylinder has inner radius of R2 and outer radius of R3. And now we will see that how exactly this figure is there. And one thing which is important that we have already discussed is the contact pressure P is generated at the junction of two cylinders. So we will be recalling our Lamb's equation for the analysis. So these are the Lamb's equations which are already derived. Okay, means already we have studied this. Now first of all we are focusing only on the inner cylinder. So if you see the inner cylinder, then for the inner cylinder the contact pressure will behave as an external pressure at the radius R2. So what will the inner cylinder will only feel the external pressure P, which is nothing but the contact pressure. Okay. So first of all we will only consider the external pressure. Considering external pressure only. Then what we will do for the external pressure, Pi will be equal to 0. So we will update these two equations. Sigma T is equal to minus PO RO square divided by RO square minus RI square plus RI square upon RO square divided by X square minus PO divided by RO square minus RI square. So once we modify this and if we go to the final conclusion, then is equal to minus PO RO square divided by RO square minus RI square into 1 plus Ri square divided by x square. So this is the value of sigma t, which is obtained from this equation. Okay. Now similarly, for the radial stress, we can put the value of Pi as 0 in this equation and obtain a similar kind of equations that I am writing down directly. Sigma r is equal to minus PO RO square divided by RO square minus RI square into 1 minus Ri square upon x square. So this is the equation when we only consider the external pressure. These all are very important equations. Now we will obtain the same equation again for the consideration of internal pressure only. So why we require this, let me show you again. Now I will also require these two equations again. So if you see carefully here, then for the outer cylinder, that contact pressure P will only behave as the internal pressure, completely reverse than the inner cylinder. So for that we need to consider only the internal pressure. So in such case PO will be taken as 0. So again now we can modify these two equations. Sigma T is equal to Pi Ri square divided by Ro square minus Ri square plus Ro square minus into Ri square divided by x square minus Pi upon rho square minus ri square. So taking the common terms outside, pi ri square divided by rho square minus ri square 1 plus, actually I think it will be why I have written here minus, this is wrong, now it is correct, plus rho square upon x square. So this will be sigma t. Similarly, we can obtain or we can update this sigma r. So sigma r is equal to pi ri square divided by rho square minus ri square into 1 minus rho square divided by x square. So this is one more equation that we have obtained. So if you are understanding this, then these two equations, let us denote them as equation A, equation B, equation C, and equation D. So if you understand this, then this is for the inner cylinder. These two equations are for the inner cylinder and these two are for the outer cylinder, and we are deriving this theory purely based on the Lenz's equation. Okay, so I hope you have got this. This A, B, C, D equations are very important for our derivation purpose. So let me first copy them. Now we will move forward. Now what we will do is we will first discuss about the inner cylinder, that is based on the inner cylinder equations A and B. So here we will be finding out the tangential stress at the inner surface of the inner cylinder and radial stress at the inner surface of inner cylinder. So let's begin. tangential stress at the inner surface of inner cylinder. So for that, what we need to do? For that purpose, instead of this x, we need to put R1. So if we see this equation, then in this equation, for the equation A, instead of P0, we will be putting P. Instead of R0, that is outer radius will be in this case R2, Ri will be equal to R1, and instead of x, we will have R1, because we are focusing on the inner surface of the inner cylinder. So here sigma T1 is equal to, we will simply put all these values in equation A, minus P into R2 square divided by R2 square minus R1 square into 1 plus, instead of Ri we have R1 divided by, instead of x we can put R1. So the final equation will be sigma T1 is equal to minus 2p R2 square divided by R2 square minus R1 square. So this is the first equation that we have obtained. Similarly, we can calculate the sigma R1. Sigma R1 is equal to, now we will update the equation B, minus P into, instead of R0 we have R2 square upon R2 square minus R1 square into 1 minus, instead of Ri we have R1 square divided by, instead of x we have R1 square. So as you can see that this term sigma R1 will be equal to 0. So we have calculated the tangential stress, and this is the, this portion is radial stress. Okay, now let's copy this portion in our slide. So we are ending this fourth lecture here. Thank you so much for watching this video.